Hi, welcome to this video on LLMs from scratch for security engineers. This is not yet another YouTube video that says AI is great, you have to use it everywhere and it solves all your problems. Rather, in this video, I'll help you look past the AI buzzwords and hype and help you understand what large language models are. I'll explain it in simple terms and give you pro tips and practical examples along the way. Also, if you stick till the end of this video, I'll give you my thoughts on where you can use LLMs and where you shouldn't. Let's get started. My journey with LLMs began when I was writing this article called so-called AI-powered cloud security. In this article, I described different ways on how cloud security vendors are actually using AI and then what are they actually delivering. A spoiler alert is most of them are just integrating some kind of large language model and call their product AI. Now it is one thing to critique, another thing to understand it and see if it works or not. So I had to get my hands dirty to understand what large language model is and then try to build up apps and try to see it for myself if LLM actually solves a cloud security problem or it doesn't. First things first, what is artificial intelligence? Now let's look at two angles, the top down one and the bottom up. Let's try to define artificial intelligence. If you look from the top down or a very high level holistic view of artificial intelligence, it is simulating human intelligence by machines. So it's all the atoms that you make to ensure that machines simulate the human intelligence and try to enact or try to do what you would do. If you look at the academic branches, you would find things like natural language processing, machine learning, and deep learning, and there are a few more under artificial intelligence. However, if you look at the applications of it, like look at the bottom up approach where you look at the applications in the market and come up with a technical definition of what artificial intelligence is, it becomes quite tricky because AI is being labeled on multiple applications and not all these applications are very similar. For example, you have self-driving cars, you have facial recognition, you have robotics, which use some kind of artificial intelligence to do certain tasks. It's pretty hard to come up with one silver bullet for a definition of artificial intelligence that covers all the applications in the market. The first pro tip to you is if there is anyone coming to you and saying that our product is AI powered, the first thing that you ask is explain what AI means. Like, are they talking about large language models? Are they talking about customized machine learning models or something else, something in between? You don't know. You can't make an assumption that, okay, they are using something that is good. And also ask about the performance of the so-called AI and how it is performing for your particular use case. Now let's get into large language models. Large language models are a very small subset in AI. So large language models are machine learning models that are part of generative AI. Are LLMs the only part of generative AI? The answer is no. You have other models which are fine-tuned for other data types. For example, you have different models to generate text. You have different models to generate images and videos and audio. And LLM is just one part of generative AI which generates text. If you try to define large language models, they are just pattern prediction systems. They try to come up with what is the next most probable word and then try to complete the sentence. It doesn't understand if the data is factually correct or not. It doesn't understand the literal meaning of a word. It doesn't understand if the data that is provided is accurate or not, if it is biased or not. But all it knows is it can look at the language, at the past text and find patterns with it and then try to predict the next word if you want to complete that particular sentence. These large language models are machine learning models. However, they are not specific for one particular task. Let's say if you're dealing with security products that are into anomaly detection or let's say bot detection, they are very fine tuned or they are very specific models that are for a specific purpose. Like you can't take an anomaly detection model to go ahead and use it elsewhere because that is focused on the logs that is generated and it just looks at that one type of log or certain types of log. These large language models are very general purpose. You can ask it to create a poem or story, or you can also ask it to debug a code issue that you find with your application code. It will go ahead and try to solve it. It will try to predict the next word that might go ahead and solve your issue or create a good poem or story. How can a system go ahead and understand the complexities of language and try to predict the next word? It would depend on the training. These large language models are trained on huge number of texts. It includes books, blogs, Reddit posts, a lot more. So essentially, what these large language model companies, what they do is they just go ahead, scrape the internet, get the data, and train the models. Training models are very time consuming and compute intense tasks. So it costs few $1 million every time you need to train a model. But once you have the training data and you have completed the training, you get something called parameters. This is one important component of LLMs. This parameters is huge numerical value that encode complex language patterns. For example, it doesn't understand the grammar rules within a language, but looking at the data, it knows, okay, if I use a particular tense, then the sentence completely uses the same tense. Or if I use the word cloud platform, somehow AWS and GCP and Azure are related to cloud platforms. Maybe if you ask what are the examples of cloud platforms, it can go ahead and predict, even though it doesn't have the context or it doesn't know what a cloud platform is. So parameters understand these kind of complexities within a particular language. You can always come across these parameters like in the image where every model that you see, there will be some parameters associated with it. For example, GPT-2 is 1.5 billion parameters. GPT-3 has 175 billion parameters. There are other things like Lambda and Bloom. Parameters are just one core component of large language models. You can't directly interact with that. Rather, you need to use the other component called inference engine. What inference engine does is it tries to handle everything, including the parameters. So it tries to initialize the model. It goes ahead, gets the input from the user, converts that English words into tokens, sends it to parameters, finds the next predicted word, gets the token of the output, and then converts back to English. So to give a simple analogy, you can think of it like a runtime. This is just for your understanding. I'm oversimplifying here. Inference engines acts as the runtime for parameters. So you have to use inference engine to go ahead, give your input, and then that does the task and gives you the output as well. For an LLM to work, you need both the parameters and inference engine. If you just have one, then you don't have the complete LLMs. If you just have parameters but not the inference engine, you can't do much with it unless you build and optimize your own inference engine. But on the other hand, if you just have an inference engine but not the parameters, again, that's not going to make a lot of sense because you have nothing to predict what's the next word. If you remember Llama leak that happened in 2023, this was the exact reason. When Meta AI released Llama, they just released the inference code. That was public. Researchers can go ahead, tweak the code, try to do something with it. However, the parameters, the weights, which are synonymous to parameters, so that was not released, which means the inference code was public, but users can't do anything with it unless they have the parameters. And around March 3rd of 2023, someone leaked these weights or parameters on a torrent site and then posted the same on 4chan. This leak allowed anyone on the internet to go ahead, download these parameters, and use the public inference code to run a large language model completely locally. Obviously, they need to have the CPUs and GPUs to execute or run the inference engine. Let's quickly go ahead, take a look at large language model outputs and look at how it predicts the next word. I've logged into OpenAI's Playground and I'll go ahead and try to enter some text. I'm using GPT 3.5 Turbo Instruct model. Let me go ahead, try to write something and ask it to complete the sentence. Rock, paper, scissors, pick on. Now I also set the probabilities to full spectrum and set the length to a minimal value so that it just doesn't go and give random text. I click submit and I get rock. Rock has a huge probability compared to paper and scissors. Let's say, let's retry it. This also says rock. Let's retry a couple of times. It said scissors and rock again. Now you can see that there is probabilities associated with the words that it generates. And if you use this particular model, GPT 3.5, there is a huge chance that it selects rock most of the time. And you can see from this dashboard, there are things like temperature and topic. We will go ahead, look at that, and try to alter that and see how the output looks like in some time. Let's get back to the presentation. In this example, I showed what is the probabilities of the output that gets generated, but I didn't show where the LLM parameters are or where the inference engine is. That is because any proprietary LLMs that you use, Claude, Sonnet, or OpenAI's models, all these are abstracted. They are not given to the public. Public can only interact with that particular LLM using APIs. So think of it this way. These large language model companies are not giving their inference code or parameters to the public. Rather, they're abstracting the entire thing, which includes the compute needed to execute the AI models or LLM models and give the output. They're abstracting the entire thing and just give you an API. What you can do with the API is just select which model you want to interact with and give in input and get the output back. A security best practice when it comes to using proprietary large language models is don't share any kind of customer PII or any kind of sensitive data with the large language models. Like, think twice before you go ahead and add any sort of code or any sort of data with your prompt to the large language model, because you do not know what happens next. If your API keys are leaked, maybe that leads to a data leak or a data breach. Or if there is any sort of vulnerability with the proprietary LLM provider, a simple IDOR can allow attackers to look up your data. On the other hand, you have open weight or open source large language models. The difference between open weight and open source is open weights are where the parameters are available, but you are not given the permission to go ahead and use it in production for commercial purpose without explicit licensing, of course. But talking about open source, they are completely open source. The weights, the inference engine, everything is open source, probably under a MIT license. You can just go ahead and use and tweak the large language models as per your requirements. With open weight or open source LLMs, you get to host the entire thing within your cloud or data center. So the machines running the LLM inference stays within your premise or within your cloud, and your applications and the data that it sends to large language models also stays within your cloud or data center. Now, which large language model should you use? It completely depends on the use case. Should you use proprietary large language models or should you self-host it? Should you use a large language model with the most parameters or should you just go with the minimal one? It completely depends on your use case. With every model, you will have a description saying what the model is trained for and what it is fine-tuned for. For example, there are models that are heavily fine-tuned for code generation. If your use case is to generate a lot of code or go ahead and look at code with the help of large language models and try to fix it, then you look at models that are fine-tuned for generating or looking at code. Or if you're looking for creating poems in a particular language, then you look at large language models that are trained on that particular language. One thing to note here is using large language models to generate something will have the same tendencies and biases like the humans whose data was used in the training. The second part is LLMs comes with different parameter sizes. You could have LLaMA, which is 7 billion or smaller than that. Like, for example, if you look at LLaMA 3.2, you have LLaMA 3.2 with 1 billion parameters, 3 billion, 11 billion, and 90 billion parameters. Using a model with bigger parameters doesn't necessarily mean that it is the best in class solution for your use case. Bigger parameters just means it is capable of handling a wide variety of tasks. Let's say you have 100 tasks which are completely different. Talking about creation of poems, creation of stories, creation of code, and creation of whatever. So if you have, let's say, 100 different tasks, then the models with bigger parameters are able to complete a huge number of them compared to the smaller parameter models. If your use case is very specific, let's say you want to generate policy as code documents using natural language, then you can check your use case, or you can test your use case with different llama models, especially those with the different parameters, and find the one that works best for you. Just because there is 90 billion parameter doesn't mean you have to use it right away. You can test it with 1 or 3 billion parameters and see what is the increase in accuracy when it comes to using bigger models. If the difference between the 3 billion large language model and the 90 billion large language model is just 2 or 3%, that is negligible. That is because for a bigger model, you would need a lot of compute to run it. So my recommendation is you go ahead with a smaller model that does majority of your work, and go with a higher model only if you have a huge accuracy gain. Pro tip number 2, as I mentioned before, find an LLM that works best for your use case. Just because others say that, okay, this particular model with this particular parameters is amazing, it doesn't mean that you have to use it right away. Find your use case and then test it across different LLM models. Now let's say you found the right large language model. The next step is to get better output from the model. There are two things that you can do given that you have already selected the right large language model. Number one is update configurations of generating the output, and second is update your system and user prompts. We will look at these two things now. First is configuration. With any large language models, you have two really important configurations. One is temperature and the next one is top peak. Temperature is a configuration that defines the randomness of generated text. Temperature is just a number between 0 and 2, and it defines the randomness of the generated text. If you set the temperature to 0 and try to execute an input maybe 1,000 times, you are going to get very similar answer. Not the same, but very similar answer. And it's not really random. It just tries to give the same output or very similar output. But if you set it to 2, the generated output is more random and sometimes even weird output. In this example, you can see that setting a high temperature and asking to complete the next word or predict the next word after sports, LLM might give past or might give any of these which has lower probabilities. However, when you set the temperature low, it kind of picks the one with higher probability. Let's look at a demo. I go to playground again. Now I'll use the same example. Rock, paper, scissors, pick one. The default temperature is set to 1. Let's go ahead, execute it. It has rock. Let's execute it again and see. It also, okay, now it generates paper, even though it had like 36% probability. And do the third execution, it says rock. So we executed it thrice. It generated rock twice and paper once. If you remember the previous execution, it had rock 4 times and scissors once. Now let's set the temperature to 0 and go ahead and execute it. Rock, rock, rock. When you set the temperature to 0, it always picks the next word with a higher probability. So it reduces randomness and it is more deterministic. Now, if you run this code 1,000 times with temperature 0, it is always going to predict rock. But let's say if you set this temperature to 2 and see how it performs. So it just gives something completely random. Like it's not selecting anything from rock, paper, scissors, rather it's selecting some gibberish words. Like it's different. Okay, it's not making sense at all. It's just generating something pretty random. It's not selecting an option from what we give it to the large language model. The second configuration is top P. Top P is a configuration whose value can be anywhere between 0 and 1. And this defines how many possible words to consider next. Like let's say if you have sports, and when you set the top P to the maximum, which is 1, then the next one is selected from a huge variety of options. Like it could be in and worldwide or activities. But if you start decreasing the value of top P, it decreases the choices of words. Like if you set the top P to 0.91, it might decrease it to just in and comma. Now let's quickly go ahead and check it in the playground. Now let's set this to the default value, which is 1. Or let me try a different example. So whether today is with top P set to 1. The weather today is very nice today. Okay. It's 20 degrees. It's sunny and warm. It's cloudy. So you get to see this, right? It's giving a lot of example. It says sunny. It says it's cloudy. It's sunny with a light breeze. It says sunny with a light breeze. Okay, it's kind of okay. I just didn't remove this. It's most likely cloudy. Okay. Now let's go ahead and reduce it to 0 and see what happens. It's sunny and warm. Sunny and warm. So it is repeating the same words. It's just repeating the same. So if I set the top P to 0, it is kind of repeating the same and it is choosing the best next word. A recommendation from OpenAI is don't alter both, don't change both temperature and top P, just change one at a time and see what works best for your use case. If you are into writing and you want some creativity, try to change temperature. But if you're looking at generating factual data or data that is very similar to that written in textbooks, then you can play around with top P. Next is prompt fine tuning. LLMs work with tokens. They don't work with English language. Rather, they convert these English words to tokens and then try to predict the next better word. Let's take a look at how tokens are. Let's say, hi, how are you? You can see that this sentence is split into 5 tokens. Hi, and the punctuation is a token in itself. And how are you? If you look at the token IDs, they are converted to this one. Let's try to see. You can see that you that I'll put here has the same token ID, of 481. If we select a different model, let's say GPT 3.5, the token IDs for it changes. Now that doesn't mean your input would always be converted to same number of tokens across large language models. Let's take another example. Give me the state of the art iPhone. Look at this. Here it has 9 tokens, but when we go to GPT-3, it considers this as 11 tokens because it considers hyphen as different tokens. There are two things when it comes to interacting with large language models, that is system prompt and user prompt. You can use either of it, but when you interact with large language models, there should be at least one prompt that is sent to the LLM. Both system prompts and user prompts are just instructions on what the LLM must do, but the bigger difference between the system prompt and the user prompt is system prompt provides the context or the tone or the responses or other additional knowledge to the large language model, whereas user prompt is just asking for certain queries or asking for execution of certain tasks. Now, another thing that you have to keep in mind is the token limit. Every large language model has some kind of token limit, and if you are breaching that limit, meaning your input is greater than that particular token limit, a good chunk of your input may not be processed by large language models or might not be used while generating or predicting the next word. So just keep in mind about the context window token limit and the max output token limit as well. This would impact your generation or prediction of the next word. Let's quickly go ahead and take a demo of AI powered Hello World program. I'm using Google Colab server to execute it. It is connected. Let me go ahead, fetch the OpenAI key from my environment variables. I've set the OpenAI key in the environment before this demo. So I just fetch it from the environment variable, install the OpenAI library, I guess it is already installed. Hide it, create the OpenAI client. And now I set two prompts. One is system prompt and the next one is user prompt. System prompt says the users purchased this particular product called Cloud 6 sunscreen product just for this demo purpose. And it says it was purchased on 1st Jan 2025. And I also said don't try to answer any other questions apart from the sunscreen. And in the user prompt, I'm asking what is the cost of iPhone. So I execute this. This is again stored on the local system, but it is not yet interacting with OpenAI. Let me go here, add my system prompt as well, and try to generate the text. Now it says I'm here to help with questions about sunscreen because we have set a system prompt that says that, okay, just answer questions related to the sunscreen, but nothing else. But when I say questions like, when did I purchase the sunscreen? Execute this and check the response. It says you purchased on 1st Jan 2025. I could ask questions like, what was the name of the sunscreen? What was the name of the sunscreen? And like, send it. The name of the sunscreen product you mentioned is Cloud 6. Now, if I just remove the system prompt and just send the user prompt to OpenAI, look at the response. You didn't mention any specific sunscreen in your previous messages, so it doesn't know what we are talking about. Let's get back to the presentation and look at fine tuning the prompt. There is this concept of zero shot, one shot, or few shot prompts. You can think of it like giving examples. Large language models are good at performing zero shot tasks, which means you don't have to explicitly give information before asking it to perform a particular task. For example, let's say you want to convert YAML to JSON or JSON to YAML. You don't have to explain what YAML is, what JSON is. Just give the prompt and ask it to do a conversion of a minor YAML file to JSON. It just goes ahead and does it. Zero shot tasks, while it is good, have its own downsides. These zero shot tasks may not be very good when it comes to tasks that involve some kind of logic. For example, math based task where you give it a question saying that, okay, this is the question and what is the answer. LLM, instead of trying to come up with a logic, it might just go ahead and like predict some number as the answer. One shot or few shot prompts will help you with those scenarios. One shot or few shot prompts is where you give examples of it and then ask for the answer. Like in this case, you can see it's a few shot COT. COT means chain of thought. We will look at that in the next slide. You have the question and you have the answer. This is an example that is provided where you are giving the logic on how it works and you're giving the answer, the expected answer, and then you ask the task to be performed. Then the large language model predicts what could be the answer for this math problem or what could be a solution for the problem that you're trying to solve. Next in prompt fine tuning is chain of thought, where you ask it either to give step-by-step instruction or you give few examples and then ask it to generate the answer. You can see in this zero shot chain of thought example where you just give the question and ask it to think step by step. It generates an answer. It There could be times when the chain of thought itself is faulty and it gives you a wrong answer. Depending on your use case, chain of thought might work. Asking it to solve the problem step by step might give you a better solution. Few short chain of thought is where you give example and then ask it. With the small programs that I've created to interact with large language models, I've seen better output when I supply a few examples in the prompt and also ask it to go ahead and solve it step by step. Okay, to quickly recap what we just saw, if you have a particular use case where LLMs can solve it, then first step is pick the right LLM that works for your use case. Try to play around with temperature and topy to generate better outputs. And the third thing is possibly use both chain of thought and a few short prompts to generate better answers. Now let's go beyond large language models. LLMs have some inherent problems with it. Number one is it has old data and the data that was public. For GPT-4o, the knowledge cutoff is October 2023. Any data that was public before this date, maybe the large language model knows about it, but anything that came after it, large language model has no clue. For example, AWS released a feature called Resource Control Policies, RCPs, which is a part of AWS organizations, and that could be used to go ahead and set guardrails and secure your cloud accounts. Now, if you ask GPT-4o, without asking it to browse the internet, if you just ask it to give a solution on how you can secure your AWS organization, it provides just SCPs and not RCPs, because GPT-4o doesn't know that there was this new feature released by AWS. Similarly, the news articles and the documentation that the LLM model was trained on might be pretty old now or even deprecated. So that is one problem. And the second problem is text generation isn't sufficient. Large language models are good at predicting the next word. You can fine tune it, you can try to tweak the parameters and the prompts and try to generate text. But again, if you look at it, the generated text, you need someone to take action based on it. Probably a user who looks at the output and takes action. So these are two inherent problems with large language models. To solve the first problem of not having the current knowledge about things or not having information about your internal projects, that is where retrieval augmented generation comes into play. Retrieval augmented generation, or RAG in short, is a fancy way of saying that you are also going to send the context along with the system prompt. Instead of directly interacting with the large language model, you are going to interact with the program. Now, what this program does is, if you ask a question about your internal projects or something that is private to your startup, it goes ahead, fetches the relevant documentation and sends it in the system prompt. And whatever question you have will be sent as part of user prompt. LLM will just go ahead, look at the system prompt and the user prompt and come up with a relevant response. In a multimodal RAG, it increases the places where it looks. It's not just looking at text, but it also looks at images, it looks at videos and audios and finds more information about your query and sends that in the system prompt. The only thing that changes with a multimodal RAG is the number of places it looks, the number of data types. It's not just text, it also includes audio, video, and images. RAGs kind of solved the first problem with LLMs, where it had a knowledge cutoff date and it didn't have access to your internal projects during training. For the second problem, where you need some humans taking action based on the output, that is where AI agents come into picture. AI agents allow taking actions, example, writing code or executing external tools. They could be semi-autonomous, where you can give some instructions like, okay, if you do this, then do this, or like you execute the first prompt and then the second prompt and the third prompt. Or it could be completely autonomous, where you give the decision making authority to large language model, and whatever is the output, the AI agent would just go ahead and execute it. AI agents are especially useful when we are talking about open-ended problems, where the steps to solve the problem is not defined. Like, example, fix the code. You are not going to define the problem, like what is the problem. Instead, you just give the code snippet and ask it to go ahead and fix the code. With all this context on large language models, finding the best model and then fine tuning the prompt and the configuration of it, now we come to large language models and security. Let's start with the practical personal examples that I use. I use for summarizing text. There are lots of blog posts. There are lots of new features coming up with, say, AWS or other cloud providers. I use it to summarize text and get a gist of it. And if it is interesting, if it's a good read, then I go through reading those blog posts or articles. Second is writing and vocabulary. And, and the third way I use is retrieve data from personal notes, be it red team engagements, pen test, or freelance engagements, where I have some knowledge already in my notes and then use that to build or to come up with newer ideas. Talking about practical examples that I've seen with companies or I've experimented it myself is offensive tasks. Large language models are useful in offensive tasks that involve some kind of natural language. For example, social engineering or phishing or vision. Code generation or pipeline generation, policy or query generation is another example where large language models are pretty helpful. I've also seen blog posts on malware and red team tool development. End of the day, malware and red team tools are essentially code. So code generation helps a lot with development of these. Finally, threat modeling and design reviews. The concepts like Stride remains the same, but the underlying systems would differ. So you could ask large language models to go ahead, look at the code and come up with the threat model, or do a design review of it. And while it does not do 100% of the threat model or the design review, it does to a good extent. It finds most common issues that could have been missed due to human error if you're doing it manually. So these are the examples that I've found so far that I use personally or that I've seen it work. Looking at all these practical examples and my personal examples, I have found a particular pattern where we can use LLMs or where we shouldn't use LLMs that I personally follow. LLMs are useful when we have non-recurring, unstructured, random inputs that can't be automated and the produced output is not detrimental. Let me break this down. Three important things here: non-recurring, unstructured, and random inputs. It could be all of it or it could be just a combination. Let's say if you have a non-recurring task that's there, it's just an ad hoc task, you just do it once and be done with it, then there's no point of automating it. You can just use large language models to solve it and do it manually, or use large language models to go ahead and create the code for it and execute it. The second one is unstructured. Example could be find the sentiment from this data, and all you're giving is a lot of strings. In that case, the strings are not really structured. You can use large language models to process it and come up with the sentiment of that language of or that sentence. And the third one is random inputs. This is where large language models are better than the classic machine learning models, where it can handle a lot of random inputs. Let's say an example is your CISO or your manager is asking different kind of questions. One day your manager asks for a particular question and the next day he asks a completely different question and the third day he asks to create a program. If the inputs are pretty random, large language models can help there. And the last part is also important, where the produced output is not detrimental. You can use large language models with necessary guardrails to ensure that the output doesn't cause any kind of impact. Let's say if you're using large language models to run SQL queries, ensure that your system prompt doesn't allow delete queries or drop tables. So using this pattern, the good examples I found are idea to code, query, image, or text, where the idea is pretty random, it is not structured, and it could be recurring or non-recurring, depends on your ideas. The second is contextual actions, where it is unstructured data. You can just say that, okay, this particular project X is going to be deprecated within a month. Now, if that is the context, maybe large language models can go ahead and suppress all the security findings for project X for a month. Similar pattern applies for threat modeling, design reviews, or understanding or using LLMs to understand workflows across websites. And I've also found bad examples of using LLMs. I'm saying bad examples because let's say if you remove large language models and don't use that as a solution, these problems can still be solved in other ways in more deterministic fashion. Examples are replacing well-performing custom-built ML models, replacing that with large language models. Now, if you have a specific ML model to solve a very specific issue, then those ML models are much better than large language models. Second example is replacing dashboards. LLMs should never replace dashboards because that's a recurring thing that you keep on seeing. And the third one is using AI as security tools. If you ask an AI to do a list of checks on your cloud account, it might come up with 10 checks and go ahead do it. But when you ask the same prompt with the same model again, it might come up with 12 checks. Now, there is no consistency with these results. It is better to use security tools that are created to solve those problems rather than trying to use large language models to go ahead and solve those. So that's it in this video. I hope this video was informational. If you have any sort of doubts or questions, please do leave it in the comments below.